On a September morning in 1859, English astronomer Richard Carrington was studying sunspots through special dark filters. Around 11 a.m., a blinding flash of white light erupted from the sunspots, lasting 5 minutes. But the most amazing thing happened about 17 hours later. Earth's magnetic field went crazy as a giant solar storm slammed into our planet. This wasn't your average storm. It was so powerful that telegraph systems across Europe and North America went haywire. Sparks flew, machines worked even when disconnected from the sockets, and auroras, usually confined to the poles, lit up the night sky as far south as Cuba and Hawaii. This event, also known as the Carrington Event, was the strongest geomagnetic storm ever recorded, and it showed us the sun's hidden power and how vulnerable we are to its outburst. Today, 15 solar cycles later, we face another solar drama, an early peak in the sun's activity and a possible magnetic flip. As the sun ramps up its 11-year cycle, expect more solar flares, sunspots, and coronal mass ejection. While auroras might paint dazzling displays across the sky, there's worry. Our tech-reliant world, our health, and even ocean temperatures could be impacted. This peak also coincides with the Artemis mission, humanity's return to the moon after decades. The upcoming solar maximum raises several questions. How will it affect Earth in the coming years? What worries NASA about this particular cycle? And most importantly, will it endanger astronauts on the Artemis moon mission? The sun, our life source, might seem constant with its daily rise and set, but beneath its familiar face lies a dynamic ball of hot plasma constantly in flux. Sunspots, flares, and gigantic prominences erupt from its surface. Every 11 years, the sun's activity ramps up and down in a cycle called the solar cycle. We're currently in cycle 25, observed since systematic tracking began in the 18th century. So, how do we know that the sun's activity changes? Sunspots, cooler, darker regions on the sun's surface, are the key. Caused by intense magnetic activity, they can be massive, even dwarfing Earth. Astronomers tracking sunspots noticed a fascinating pattern. Their numbers rise and fall in an 11-year cycle. They also observed changes in their size, location, and how they move. A solar cycle starts quiet, with few sunspots also called the solar minimum. Then, activity picks up with more and larger sunspots appearing near the sun's mid-latitudes. As the cycle progresses, these sunspots migrate towards the equator, eventually forming a butterfly pattern when tracked over time, as can be seen in the butterfly diagram. For years, sunspots were the only measure of solar activity. But with advancements, scientists discovered two more things that change during a cycle. Firstly, the sun's magnetic flip. The sun, like Earth, has a north and south magnetic pole. Shockingly, this polarity flips with each cycle. North becomes south, and vice versa, happening around the solar maximum and marking the cycle's midpoint. Thus, one of the sun's biggest mysteries is its magnetic flip. Every cycle, the sun's north and south magnetic poles swap places. Scientists believe the sun's uneven rotation, slower at the poles, faster at the equator, plays a part. This differential rotation twists and tangles magnetic fields beneath the surface, eventually causing them to reverse at the poles. While this flip is predictable, understanding why it happens remains a challenging problem in solar physics. Along with its magnetic field, the sun's overall activity, solar wind, flares, and coronal mass ejections, also rises and falls throughout the cycle. It's strongest at the peak, solar maximum, and weakest at the minimum. This is why monitoring cycles now include tracking activity and polarity reversal, not just sunspots. Now you might wonder, Are all solar cycles the same? Not quite. Not all solar cycles are created equal. Since we started tracking them closely, cycles have ranged from a quick 9 years to a lengthy 14. The average cycle lasts around 11 years, but the intensity varies too, measured by the number of sunspots. Scientists have even observed strange periods of very low activity, just like in the Maunder minimum, from 1645 to 1715. In this period, we saw a dramatic drop in sunspots, coinciding with the colder than normal temperatures of the Little Ice Age in the North Atlantic. Another period, the Dalton minimum, 1790-1830, also saw fewer sunspots and linked to cooler global temperatures. Then there's the modern maximum, 1933 to 2008, a period of higher than usual solar activity. Now with solar cycle 25, scientists are in for a surprise, predicted to be mild. It's showing unexpected intensity and reaching its peak earlier than anticipated. Forecasts for cycle 25, which began in December 2019, predicted a peak in July 2025 with around 115 sunspots. However, the picture has changed. The NOAA Space Weather Prediction Center now expects a peak between January and October 2024, with a higher than expected range of 137 to 173 sunspots. This shift highlights the dynamic and unpredictable nature of solar activity. To understand the impact of this intense early peak, let's look at X-class solar flares. These are the most powerful bursts of radiation erupting from the sun's atmosphere. They happen when twisted magnetic fields reconnect, releasing tremendous energy. Flares are ranked by strength, with X-class being the most intense. Class flares can cause minor issues, while X-class events can trigger radio blackouts, radiation storms, and even damage satellite. The Carrington event of 1859, the strongest geomagnetic storm ever recorded, was linked to an X-class flare. The current cycle is already surprising us with frequent X-class flares. On July 3, 2021, a major radio blackout followed the first X-class flare of this cycle. In early 2022, a powerful flare knocked out 40 newly launched Starlink satellites. On December 15, 2023, an X2.8 flare disrupted radio communication for 2 hours. On New Year's Eve 2023, the Sun unleashed an X5 flare. Similarly, on February 21, 2024, 2 X-class flares erupted within 7 hours, followed by another record-breaking X6.3 flare within 24 hours, all 3 disrupting radio signals on Earth. With the solar peak approaching, scientists anticipate even more frequent X-class flares. Now, we come to a crucial question. Does increased solar activity drive global warming? This graph offers some clues. The graph tracks Earth's temperature, red line, and the sun's energy reaching Earth, yellow line, from 1880 to 2020. Lighter lines show yearly data, while thicker lines represent the 11-year solar cycle average. Until the 1950s, both lines trend upwards. However, after that, they diverge dramatically. This separation tells us a story. Solar activity alone can't explain global warming. While it might play a role, it's clearly not the main culprit. High solar activity poses challenges for NASA's Artemis missions. Launches need to avoid periods of intense solar storms. The energetic particles from these storms can damage electronics and disrupt communication, making it difficult to control the spacecraft. However, there's a bright side. High solar activity shields satellites from galactic cosmic rays, offering some protection. These rays can also harm electronics, so this period offers a window of reduced vulnerability for satellites. On a positive note, the solar maximum boosts auroras, the stunning northern lights or southern lights. These celestial light shows appear when charged particles from the solar wind collide with Earth's atmosphere. Seeing these colorful displays is a breathtaking experience. Head to Canada, Alaska, Iceland, or other high-latitude locations to witness the auroras paint the night sky with their vibrant glow. Recently, the Voyager 1 probe is sending some random binary data back to Earth. This video explains why